available in the form of matter or radiation. And we also know that nature loves symmetry. So, when radiation is having the dual nature, another entity, matter, should also have dual nature. This was the thought given by de Broglie. And he also proposed that every moving material particle will be associated with a wave. So, we have to clearly see here the word moving. Every moving material particle will be associated with a wave. So, this itself clearly says that if a particle is at rest, there will not be any wave associated with that. So, a moving particle is associated with the wave, which will govern the particle moving in every respect. So, this wave associated with the moving particle is called de Broglie wave or matter wave. So, de Broglie wave will possess, any wave will possess a wavelength. So, we represent it by notation lambda. So, matter wave or de Broglie wave is what? It is a wave associated with material particle moving with some velocity. So, this is called as de Broglie wave, and we will just derive the expression for de Broglie wavelength. Now, we know that energy is given by h nu. This is the energy possessed by each and every photon emitted by the source of radiation. And by Einstein's mass energy equivalence, we also know this energy is mc square, where c is the velocity of light in vacuum or free space. So, equating these two, we can write h nu equal to mc square. If you name this as 1 and 2, from 1 and 2 we can equate. So, what is m from here? M will be h nu by c square. By rearranging, we get m equal to h nu by c square. And we also know that momentum, linear momentum p is the product of mass and the velocity. So, m into c. So, m we can substitute from equation 3 as h nu upon c square into c. So, which is otherwise we can write it as 1 c will be cut. So, we will have like this. So, if I am bringing that nu down, so it will become like this. We also know that c upon nu is wavelength. So, lambda will be h by p or h upon mv. So, this is the expression for de Broglie wavelength. What is h here? It is the Planck's constant, and mass m is the mass of the particle moving, and v is the velocity of the particle. Now, it is very important formula. You will be getting conceptual problems as well as numericals based on this. Now, when I stated the definition of matter wave, I made a mention about particle moving. I told you to remember the stress upon this word moving. Why? Come back to this equation, lambda equal to h by mv. Suppose if v is 0, what will be lambda? Will be infinity. Or another condition you substitute, when v is infinity, lambda will be 0. So, if you carefully look at these two conditions, v 0 means what? We are considering a stationary particle, the particle at rest. In that condition, what is the wavelength? It is infinity. That means we can't visualize the wave at all. When the wavelength is infinity, we can't visualize it or we can't measure the wavelength. Another condition says when v is infinity, that is if the velocity of the particle is infinity, which is not possible because we know that velocity at the most can be equal to the, not at the equal or nearly, it may be near to the velocity of light. So, velocity infinity condition cannot be considered or visualized. So, in that case then lambda becomes 0. That is also says that no waves is associated, no wave is associated with the particle, even if it is moving with the infinite velocity. That means this clearly tells you that first condition clearly tells you that the matter wave or de Broglie wave comes into picture only when the particle is moving with some velocity. That is why we gave a stress on this word moving. And one more question arises here, that when we say de Broglie wave, can it be electromagnetic wave? So, how to answer this question? Now, when we say this de Broglie wave, de Broglie observed that whether it is a charged particle, that is positive or negative, or if it is uncharged particle, whatever it may be, that is immaterial of the charge on the particle, every particle moving with some velocity will be associated with the wave. That means it is charge independent. But what is electromagnetic wave? Electromagnetic waves are emitted by the accelerated charged particle. So, because of that source of EM wave we have studied, this de Broglie wave cannot be EM wave, because this wave will be associated, matter wave will be associated with every particle moving, that moving is important, moving immaterial of the charge on it. So, this clearly shows that de Broglie waves are not EM waves. So, next we will see how this de Broglie wavelength is related to the temperature. So, next we will see how the de Broglie wave is associated with, de Broglie wave is related to the temperature. So, we know that the kinetic energy associated with a particle at a temperature T is given by 3 by 2 kT, where small k here is a Boltzmann constant. T is the absolute temperature. So, this we have studied from kinetic theory of gases, we have studied in 11th standard. Then kinetic energy also can be written as we know half m v square. So, when you equate these two, or we can rewrite this, we will get v from here. What is v from here? V square will be 2k by m, or v will be under root 2k by m. Now, substituting k from this equation, suppose if you are naming it as equation 1, 2, this 3. So, this v actually we have to write it as small v, because it is velocity. So, capital V will be representing the accelerating voltage. So, we will write small v here. So, substituting k from 1. We get v equal to so this 2 will be cancelled, and so v will become 3 kT by m. Now, we know that mv momentum p mv will be under root will come here, because only 2 is cancelled here. So, this under root should come here also. So, m into v if you substitute. So, taking this m inside, we will square and take it. So, this will become m square 3 small k t upon m, 1 will be cancelled. So, you will get 3 m k t. So, that substituting this here for mv, de Broglie wavelength will become. So, this v here actually is the constant velocity. So, the particle is not accelerated here. That is why I made a mention that de Broglie wave is not a electromagnetic wave, because electromagnetic waves are emitted by the accelerated particles. So, in this equation v remains constant, there is no acceleration. So, the de Broglie waves associated with a moving particle is not the electromagnetic wave. So, we can substitute mv from here. So, we will get h upon under root 3 m small k t. So, this is the relation between de Broglie wavelength and the temperature. So, in the numerical you have to see which are the factors given, which are the data given, accordingly you will choose the formula. So, lambda equal to h upon under root 3m small kt. Small k is the Boltzmann constant, capital K is the symbol for the kinetic energy we are using. Sometimes in the numerical, if you see carefully, if you read it, they will be mentioning about electron. So, we can derive the expression for kinetic energy of electrons especially. If you know that formula, and in the numerical if electron is the particle mentioned, you can use this simple formula easily and solve the problem. So, we will see that de Broglie wavelength of electron. I will use this symbol for wavelength of electron. Suppose electron of charge E is accelerated by potential difference, that is PD capital V here, then what is the work done on it? It will be charge into PD, that is E into V. And if the kinetic energy gained by the electron is half mv square, this work done by the accelerating potential capital V will be equal to the kinetic energy attained by the electron. So, we can write like this. So, from here you rearrange and get velocity. So, we have to clearly mention the difference here, that is when you write equation involving two V's, one you write with the capital V representing the accelerating potential, another with small letter v to represent the velocity. If you are writing the same this thing, by mistake you may cut these two. So, that should not happen. So, please be careful while writing these symbols. So, V square will be equal to 2 EV upon m. So, what is V from here? Under root 2 EV upon m. Again you find out momentum, that is P equal to mv, m 2 E capital V by small m, again taking m inside, m square 2 EV upon m. So, this will become 2 EM V. This is momentum. So, what is de Broglie wavelength? We know lambda equal to h by p. So, h upon under root 2 EM into V. So, if you carefully see this equation, excepting this capital V, which is the accelerating potential which we give in the apparatus, other things are constant. 2 you know the number only, h is a Planck's constant, E is the charge on the electron, m is the mass of the electron. So, these are all constants. Substituting those values, h is 6.63 into 10 power minus 34 under root 2 into electronic charges 1.6 into 10 power minus 19, mass of the electron 9 into 10 power minus 31 kg V. So, if you calculate these values, it will come in terms of angstrom unit 12.27 under root capital V angstrom unit. So, this is a very simple formula, because all these constant values we know already, and if you are calculating it earlier and keeping the result. So, instead of remembering these many constant values, we can just remember this 12.27 under root divided by under root V. What is this capital V here? Accelerating potential. So, if in the question they will ask you, if the electrons are accelerated by this potential, calculate the de Broglie wavelength associated with that. So, this will be the simple formula, we will be using it to get the value, but we have to remember that this formula involves angstrom unit. So, in the SI unit if you want to convert, after calculating this into 10 power minus 10, we have to write, so that meter, अच्छा वो आवाज़ आ गई यहाँ से, okay. So, using this formula we can calculate easily if capital V is given, and this thing we have to remember that this formula will give you the wavelength in angstrom unit. So, to convert into meter in SI unit we have to multiply by 10 power minus 10. So, this is the expression for de Broglie wavelength of electron. So, we should not forget that this formula is used only for electron. For other particles we have to use the previous formula, in which other data also will be given to you. Now, de Broglie gave this hypothesis of dual nature of matter. We know that in science any hypothesis will be accepted only if it is proved experimentally and using mathematical equations and everything, it should be proved theoretically also. So, this hypothesis given by de Broglie was proved experimentally by Davisson and Germer. So, we will see next Davisson and Germer experiment which gave support to the de Broglie hypothesis of dual nature of matter. Davisson and Germer, they designed one setup and for supporting the de Broglie hypothesis or give the evidence to the dual nature of matter, and they just utilized or they just compared the behavior of electrons when they fall on the metal surface with that of X-ray diffraction. We have studied in wave optics that diffraction is the phenomenon exhibited by the waves. So, if electrons falling on the metal surface and the scattered electrons are giving the same wavelength experimentally with that given by the de Broglie's hypothesis, that is theoretical formula, if these two values agree in good what do you say, if there is a good agreement between these two values, that is experimental value and theoretically predicted value, that will give correct explanation or the proof of dual nature of matter. That only Davisson and Germer did using this experimental setup. So, Davisson and Germer experiment to prove the dual nature of matter. So, here they took the material particle as electron and they used the phenomenon like X-ray diffraction. They just compared the behavior of electrons with that of X-rays. If X-rays are passing through the grating where the spacing between the two lines are very, very small, we know that for diffraction to take place, the condition is what? The slit width should be approximately equal to the wavelength of the incident radius.